Welcome back. Last time we derived the Marchenko-Pastur law, which describes the eigenvalue distribution of the sample covariance matrix. Today we'll look at the same distribution from another perspective using statistical mechanics. We'll see that the eigenvalues behave like interacting particles that repel one another. And when we look at the population of the eigenvalues, they start to form the Marchenko-Pastur distribution. Okay, so let's first do a quick recap of the Marchenko-Pastur law that we derived last time. So we start with a random matrix X, whose dimension is P by N. So nice way to think about this is that if X is a data matrix, then P can be the number of features and N can be the number of data points. Then the entries of the X matrix is random with mean 0 and variance 1. And the entries are independent. The MP law says that the eigenvalue of the sample covariance matrix given by sigma equals to 1 over n times XX transpose, it has a limiting distribution known as the Marchenko-Pastur distribution. So the density of the distribution is given by this formula here. And this is what the picture looks like. And very importantly, it is obtained when both P and N goes to infinity. And we need the ratio between the two, defined as gamma equals to P over N, to be a finite number. Means that it is somewhere between 0 and infinity. So if you think of X as a data matrix, this is a case when both the number of features and the number of data points are very large. Okay, so the topic this time is that we'll look at this distribution from a different perspective. So this is a probability density function of the eigenvalues, which means that the eigenvalues is denser in here and then sparser once we move further on this axis. And quite remarkably, it turns out there's a way to think of these eigenvalues as interacting particles. So for example, if we just take out one particular particle, so there will be two balancing forces acting on these particles. The first force is a repulsive force that is coming from the interaction with other particles. So we'll have a bunch of force that push these particles to the right, because it's interacting with all these particles on the left, right? So collectively, they want to push this particle further. And then it turns out that all the particles will also have a potential force. And in this case, the potential force is pushing this particle to the left. And I have plotted the potential function for this particular MP distribution. So let me just grab the picture real quick. So this is a potential function. And for the potential force, so just like gravity, right? The direction of the force is given by the negative gradient, which means that the force is pointing from the higher potential to lower potential, right? It will act to the left for this side and act to the right on the other side, right? So I think this particular, this lowest point is given by 1 minus gamma. Basically, for eigenvalues greater than 1 minus gamma, it will have the force acting on the left, and for eigenvalues smaller than 1 minus gamma, the force will be acted on the right. So this MP distribution is reached exactly at the equilibrium state, which is the case of the potential force equals to the repulsion force. And that will lead to the Marchenko-Pastur distribution. It is quite remarkable that we can think of eigenvalue in this way. So this view is also known as the Coulomb-gas. that is one of the mechanisms to generate the MP distribution. Okay, good. So now let's try to derive this result. And for this derivation, we actually want to restrain our random matrix to be Gaussian. So we still start with a X matrix with dimension P by N. For the entries of this matrix, Xij, we want that to follow normal distribution with mean 0 and variance 1. So the idea of this derivation is that we want to start with a probability density function for the random matrix. So basically that is given by the joint probability density of the entries. So the MP distribution is about eigenvalues. So from here, we can actually apply a change of variable to obtain the joint probability density for the eigenvalues. The eigenvalues are lambda 1 to lambda p. So this step is obtained with a change of variable. So basically, we want to reparameterize the matrix with eigenvalues. And then for the next step, we basically consider the case as p goes to infinity. Then we can stop tracking this joint distribution, and then we can use a density function, rho of lambda, to describe the probability density for all the eigenvalues. And this limiting density distribution exists when we have both n and p goes to infinity. Okay, so let's get started. The first thing that we can do is just to write down the probability density for the matrix P of X, which is given by a multivariate Gaussian distribution. So basically, we have a product over I and j, and then the Gaussian density is given by 1 over square root of 2 pi, and then exponential. Then that equals to 2 pi to the power of minus p times n over 2. And then for the exponential, you can merge the product into a sum. And that equals to minus half times the sum over I and j, xij squared. Then we notice that the first term is constant. So we can write that as the density is proportional to the exponential term. And for this exponential term, there's a trace identity we can use. It's basically, the identity is basically the sum of xij squared equals to the trace of xx transpose. So it means that this density function is proportional to the exponential minus half times the trace of xx transpose. And we notice that this xx transpose is related to sample covariance, right? Because sigma is defined as 1 over n xx transpose. Trace is just the sum of the eigenvalues, which means that this trace of xx transpose equals to n times the trace of sigma equals to the sum of all the eigenvalues. So this is just proportional to the exponential minus half times the sum of the eigenvalues. Okay, so this formula is pretty neat. But this probability density is with respect to the entries of the matrix. We actually want to reparameterize this density function with the eigenvalues of the matrix. So that will require us to apply the change of variable formula. So just to recall that the change of variable formula for the probability density function So the idea is that when we have a random variable x, and we have a probability density given by p of x, and let's say that we have a random variable y related to x, the relationship can be written as x equals to gy, or alternatively we can write y equals to g inverse x. Then for the density function of y, that is given by this formula. So we use the density of x, and we need to multiply that by the derivative dx over dy. And then we also need the absolute value of that. This is a one-dimensional case although. And then for the higher dimensional, it is very similar. So this part is the same, but we need to multiply that by the determinant of the Jacobian matrix. And we take the absolute value of that. So this partial x partial y is a Jacobian. So this is a formula we want to apply. So we want to change the variable from the entries x to the eigenvalues of the random matrix. So let's do that. So the relationship between the two is given by the SVD formula. So basically we have x equals to u d v transpose. And then the eigenvalue is related to the diagonal matrix D. So the relationship is that lambda, the eigenvalues lambda I equals to the singular value square. And then we need to divide that by n. So this n comes from the factor of the sample covariance matrix. So if we want to see this, we can just plug in the formula for the sample covariance. So sigma equals to 1 over n times x transpose equals to 1 over n times u d square u transpose. So this equals to u times d square over n times u transpose. So that's why the eigenvalues is given by d square over n. But there's a relationship between the two. And now we can plug in this change of variable formula to get the joint density for the eigenvalues. So that equals to, for density function, you can just copy this formula in here. Okay, and for this equation, I think I forgot the factor n. So that basically becomes the exponential minus 1 over 2, the sum of the eigenvalues. And then we need the Jacobians. And in here, I'm not going to derive this Jacobian formula, but I'll post a link in the description if you're interested in how to obtain the formula. Here, I'm just going to write it out. So this Jacobian of the SVD formula is actually proportional to the product of the eigenvalues to the power of n minus p minus 1 over 2. And then we need another product of I smaller than j. This is the interacting part given by lambda I minus lambda j. Okay, actually this is a determinant of the Jacobian. Okay, and let's just apply this formula directly. So basically, we'll have the joint density proportional to exponential, and then we just copy this term, and then we just need to multiply that by the determinant of the Jacobian. And then for this product, we can move it inside the exponential, and that will give us summation. So we can write that as the joint density of the eigenvalues is proportional to the exponential. So first we'll have minus n over 2, and then the sum of eigenvalues. Then you have a plus the sum, and maybe let me just change this subscript to I. To stay a little bit consistent, and then we have the sum over I. We have the factor n minus p minus 1 over 2, the sum of log lambda I. And then we also need to sum over the interacting terms. So that is given by I smaller than j. And then we have the log of lambda I minus lambda j. Okay, so now this is a form of the joint density function for the eigenvalues. So we have written this distribution as an exponential with some complicated factors here. So this actually suggests a connection between this distribution and the Boltzmann distribution. So the Boltzmann distribution is generated when we are given some energy function. So let's say that we have an energy function of particles h of lambda. Then at the thermal equilibrium, we have the distribution p of lambda given by the Boltzmann distribution as some constant, as some normalizing constant 1 over z times the exponential to the minus beta times h of lambda. Where this lambda can be the position of the particles. And then the energy of the particle is dependent on this lambda parameter. So the reason that Boltzmann describes the equilibrium is because the maximum entropy principle. When you have a fixed expected energy, and that will lead to the Boltzmann distribution. So the key idea here is that we want to interpret this density function as a Boltzmann distribution. So this distribution is generated by this energy function. So now you see that our random matrix problem becomes a statistical mechanics problem. And all we need to look at is to understand this energy function. Okay, so for the next part, I'm just going to take out this energy function. And then let me just label that with h of lambda. So that equals to, so we'll have n over 2 times the sum of the eigenvalues. And then we need to subtract n minus p minus 1 over 2 the sum of log lambda I, then you have minus the sum of lambda I minus lambda j. Okay, so if you look at this function in here, and if we just pay close attention to one particular particle, lambda I, and now we can think of this lambda I as the position of the particle, right? We see that the first two terms only depend on the position of the particle, and the third term is about the interactions. So this is why we can interpret the first two terms as a potential function. And we can call this V of lambda. And then this term is about the interaction. So in StatMax, the equilibrium state is reached when the energy function is minimized. Then hopefully we'll have a limiting distribution for the particles, which turns out will be the MP distribution. Okay, so in order to find this minimum, we just need to take the gradient equals to 0. So you can take partial h, partial lambda I equals to 0. So that equals to 2 over n minus n minus p minus 1 over 2 lambda I, and then minus the sum of j not equal to I, and then we have 1 over lambda I minus lambda j. Okay, then if we just move the terms around, we'll have the sum of j not equal to I, and then we have 1 over lambda I minus lambda j. So that equals to n over 2 minus n minus p minus 1 over 2 lambda I. Okay, and the physical view of this is very interesting. So this is exactly the picture that we looked at before, that we have the balancing of the two forces. So the left-hand side can be thought of as repulsion from the interaction. And then on the right-hand side, we have the potential force. So basically, those two forces are balancing out at the equilibrium. And we noted that the force is basically depending on the position of the eigenvalues. And basically, this equation needs to hold for all the particle I. So basically, we can think of eigenvalues as one-dimensional particles. And each particle will have the balance between the two forces. One is a repulsive force when they are interacting with other particles, which is a combination of 4 particles, right, in this example. And then the other one is a potential force going to the other direction. So last time we have introduced the Stieltjes transformation. It is defined as m of z equals to the integral of rho of lambda over z minus lambda d lambda. Then for the finite version of it, when you have finite number of eigenvalues, the MP of Z equals to 1 over P times the sum of 1 over Z minus lambda I. So notice that the form of this equation is very similar to the repulsive force. It is the interaction between a particle at the location Z and lambda I. A nice way to think of this is that suppose we have a test particle at location Z. Then the repulsive force acts on Z will be the sum of 1 over Z minus lambda I. So basically this Stieltjes transformation is P times the force act on particle at the location Z. So that's a nice way to think of the Stieltjes transformation. And in order to derive the limiting distribution for the eigenvalues, we actually need some algebra. So for the next part, we are going to show the equivalence between this equation. So I'm just going to use a star here. So the next goal is that we want to convert this equation to the quadratic equation with the Stieltjes transformation we had last time. And this conversion, we need P and N goes to infinity. And P over N equals to gamma. And we'll eventually reach the equation gamma times Z times M of Z squared plus 1 minus gamma minus Z M of Z plus 1 equals to 0. And then we can just solve this equation and apply the inverse Stieltjes transformation to obtain the density function, which is the same thing as we did last time. Okay, so the next part is mostly just algebra. And for this equation that we have, we're going to look at the left-hand side and the right-hand side separately. Remember, this equation is holds for all the particles. And so the first thing we're going to do with this equation is to multiply by 1 over Z minus lambda I. Then sum over I. Okay, so this may feel like a trick, but I promise that. But by doing this, the Stieltjes transformation will show up in this equation using some algebra. Okay, so let's just do it. So we'll have the sum over I, and then sum over the pair that J not equals to I, and then we have 1 over Z minus lambda I times lambda I minus lambda J. So that's the left-hand side. Then for the right-hand side, we have N over 2, and then we have the sum 1 over Z minus lambda I. And then we have minus sum over I, N minus P minus 1, and then we have 2 lambda I times Z minus lambda I. So next for this equation, we're going to look at the left-hand side and right-hand side separately, and hopefully that will reduce to something involving M of Z. So we have the left-hand side, so that equals to, so we have sum over I, and then sum over the pair that J not equals to I, and then we have 1 over Z minus lambda I times lambda I minus lambda J. Then the next step is that we want to pair up the I and J using symmetry. So basically, for this summation, you can still sum over I, but for the second sum, so basically we have a pair of terms. So the first one is 1 over lambda I minus lambda J, and then z minus lambda I. Then we'll have another term as 1 over lambda j minus lambda I, and then z minus lambda j. Then for the ij pair, we only need to consider half of the case. So we'll have the sum over I is smaller than j. So then we can basically merge these two terms. So it's going to be sum over I, and then sum over I is smaller than j. So we'll have 1 over lambda I minus lambda j times 1 over z minus lambda I minus 1 over z minus lambda j. So actually this feels a little bit more complicated than we started. But it turns out that this can simplify. So there's a simple identity equation we can use. The identity is that 1 over a times b equals to 1 over b minus a times 1 over a minus 1 over b. So basically this term becomes so the nice thing about this equation is that we'll have exactly a equals to z minus lambda I and b equals to z minus lambda j. Then lambda I minus lambda j is exactly b minus a. So this is nice, which means that the left-hand side simply equals to sum over I, and then we have the sum over I smaller than j, and then 1 over z minus lambda I times z minus lambda j. So that equals to a half times the sum of I, and then sum of all the ij pair. Then we have 1 over z minus lambda I times z minus lambda j. Then we can replace this with the Stieltjes transformation. So the equation is that mp of z equals to 1 over p times the sum of 1 over z minus lambda I, which means that mp of z square equals to 1 over p square, and then sum over all the ij pair. Then we have 1 over z minus lambda I times z minus lambda j. So basically, if we just compare these two equations, the only thing missing is a diagonal where I equals to j. That's not included in the left-hand side. So basically, this equals to a half times p square m of z square minus p square, and then we have the sum over I, and then 1 over z minus lambda I square. So actually in this case, the second term is very small compared to the first term. Basically, this can be ignored. So the reason is that if you just look at this sum here, right? So the total number of terms, we have this sum is p times p minus 1. Then if you look at the next equation, the first part is the sum of p squared number of terms, and the second part only has a sum of p number of terms. So kind of the first term is in the higher order, right? So p squared is much larger than p when p goes to infinity. Or a slightly better argument is that the second term is actually equals to p times the derivative of mp of z. And then if we think the derivative and m of z are in the same order, then basically like that's the second term is in the order of p, which is much smaller than the first term, which is in the p square. So in the end, we'll just have a half times p squared m of z squared. So that's for the left-hand side. Okay, so let me just grab the equation. We can continue. Okay, then for the right-hand side of the equation, we see that we don't have to do anything about the first term, right? We can, that equals to n over 2 times p times m of z. Then for the second one, we can move the constant out. We have the n minus p minus 1 over 2 times the sum of 1 over lambda I times z minus lambda I. Then you can basically apply the same identity. Okay, so that will just give us, we apply left to right. You can put a minus lambda I in here and change this to a plus sign. So we apply this identity left to right, which means that this is A and this is a B. Then we have basically 1 over B minus A is Z times minus 1 over lambda I minus 1 over Z minus lambda I. So we have n times p over 2 m of z plus n minus p minus 1 over 2 over 2z. Then we have, you can change this to a minus sign again. 1 over lambda I plus sum over I 1 over z minus lambda I. So this just equals to p times m of z. Then we also need to take care of the term with the sum of 1 over lambda I. And to handle this term, we actually need to look at the force balancing equation again. So basically the force balancing equation is that we have the sum over I, sum over j not equals to I, and then 1 over lambda I minus lambda j. So that equals to the sum over I, and then we have n over 2 minus n minus p minus 1 over 2, and then the sum of 1 over lambda I. The force balancing equation is with respect to one particular particle I or the eigenvalue I. Then we can sum over all the particles I. And very interestingly, the sum will be 0. The reason is that if you look at the repulsive force, actually each force is counted twice between a pair of eigenvalues I and j. So basically when we have a pair of eigenvalues I and j, the repulsive force will go from I to j and j to I. And they are in the opposite direction. So when we sum over all pairs, each pair will have the total force being 0. So it means that this entire equation equals to 0 when we sum over all the pairs. Okay, so basically you can keep solving this equation to get what we want. So you have 0 equals to n times p over 2 minus n minus p minus 1 over 2 sum of 1 over lambda I. So this implies that the sum over I, 1 over lambda I, equals to n times p over n minus p minus 1. Okay, so now we can plug this back to the equation. So what we have is minus n minus p minus 1 over 2z times n times p over n minus p minus 1. Then you have minus okay, so this term will cancel. So that equals to n times p over 2 m of z minus p times n minus p minus 1 over 2z times m of z minus n times p over 2z. Okay, so now we can bring everything together to get an equation with respect to m of z. So let me just organize this space a little bit. Let me just put this on the side. Okay, so now this equation become a half times p square m of z square. So that's the left-hand side equals to the right-hand side have n times p over 2 m of z. Then you have minus p times n minus p minus 1 over 2z m of z minus n times p over 2z. Okay, now we can do some canceling. We can cancel the 2. We can also cancel out 1p. Yeah, and then we can multiply z to both sides. So you have p times z times m of z square equals to n times z times m of z minus n minus p minus 1 m of z minus n. Then you can divide both sides by n, right? And recall that gamma equals to p over n. This becomes 1, and this term becomes 1 minus gamma minus 1 over n. So that is approximately 1 minus gamma because n goes to infinity. Then this becomes 1, and then this p become gamma. So you have gamma times z times m of z square. Then let me just move all the terms to one side. Have minus z times m of z. Then you have plus 1 minus gamma m of z plus 1 equals to 0. So that gives us gamma times z times m of z square minus z plus gamma minus 1 m of z plus 1 equals to 0. Okay, so this is the same equation as we derived last time using the resolvent method. Basically, you can solve this equation as m of z equals to z plus gamma minus 1. Then we have minus square root of z minus a times z minus b. Then over 2 times gamma times z. And that is the Stieltjes transformation for the density function. So basically, this is a complex function. We take z equals to u plus iv. And then the density function, we can use the inverse transformation as a limit with v goes to 0. And then we grab the imaginary part of m of z. Then we also have some constant in the front. I think it's minus 1 over pi. So this just equals to, so we said that the only situation we have an imaginary part, it's for the square root term to be imaginary. So that's the case where u is in between a and b. Then that gives us, then you have the square root of u minus a times b minus u over 2 times gamma times u. So this is a density function for the MP distribution. Okay, we did it. Okay, so this is another dense derivation video. Let's just do a summary of what we have done. So we start with a random matrix X belongs to P by N. The entries of the random matrix this time is sampled from some standard normal distribution. And then they are independent. Then basically we write out the joint density function. And then we apply the change of variable to write this density function using the eigenvalues. And we see that this joint density function is in the form of a Boltzmann distribution. So that's given by the form of exponential minus some energy function h of lambda. So this h of lambda is the energy function. Then we basically want to take the minimum of h of lambda. So that gives us the equilibrium distribution. So that is the main interpretation for the Marchenko-Pastur distribution. It is an equilibrium distribution if we treat eigenvalues as particles. Then we say that the energy function has two parts. So the first is the potential energy. Then we have some interaction. And then when we find the minimum value for this energy function, and the gradient of the energy gives us the force. So we have some potential force. And it needs to be balanced by the repulsion force from the interactions. And finally, we use some algebra to convert this equation into an equation with Stieltjes transformation m of z. And then we apply the inverse transformation to get the density function for the eigenvalues. So that is the entire derivation. So across these two videos, we have looked at the Marchenko-Pastur distribution from two different perspectives. It basically describes the distribution of eigenvalues of the sample covariance matrix when our data is pure noise. So in the next video, we'll introduce a more realistic random matrix for data analysis, the spect covariance model. So this is the case when the sigma contains signal plus noise. So the key question is, how strong the signal must be for us to detect it from the noise? The random matrix theory will give us a remarkable answer for it, namely a threshold where we can reliably detect signal from the noise.